A 7-ton iron pillar has stood rust-free for over 1,600 years. This is the reality of the Iron Pillar of Delhi, a physical echo of a lost technological peak. By the end of this story, you will understand how an ancient craft could challenge our modern approach to building a lasting world. We will follow clues from legendary blades to silent monuments, uncovering why this forgotten knowledge vanished and how its rediscovery might reshape our future. How do you define true progress when the past holds secrets we have yet to master? It rises from the earth like a dark, silent sentinel. The Iron Pillar of Delhi stands over 23 feet tall, a single, unbroken shaft of wrought iron forged in the 4th century. For more than 1,600 years, it has endured monsoons, scorching heat, and the passage of empires, yet its surface remains astonishingly smooth. You can run your hand along its flank and feel not the rough, flaking texture of corrosion, but a cool, almost glass-like patina. Etched into that enduring metal are lines of Sanskrit, a proclamation of a king's devotion that has outlasted the language itself. This is not merely an old object. It is a direct statement from the past, a riddle cast in metal that asks us a simple, profound question. How is this possible? Modern science, when it finally turned its instruments toward the pillar, was met with a puzzle. Conventional wisdom stated that iron, when exposed to oxygen and moisture, must rust. It is an inevitable chemical conversation, a slow return to the earth. Yet here was a 7-ton exception to the rule. Detailed analysis revealed the pillar's secret recipe. Its iron contains an unusually high amount of phosphorus, a deliberate impurity by today's standards, and very little sulfur and manganese. This specific blend, forged under conditions we can only theorize, allowed the pillar to develop a thin, protective film. Scientists call it a passive layer, a shield only microns thick that adheres to the iron and stubbornly resists the environmental forces that would consume ordinary metal. It is a self-healing skin grown from the metal's own unique character, so we are left with a physical fact that challenges our historical narrative. This was not an accident. The consistency of the metal, the skill required to forge such a massive single piece, points to a deep, systematized knowledge. The artisans who created this monument understood their material on an intuitive, chemical level. They knew which ores to select, how to manage the furnace, and how to work the hot iron to coax out these specific properties. Their goal was permanence, a legacy meant to touch the sky for millennia, and they succeeded. But this magnificent pillar is not just a solitary wonder. It is the most famous clue, the starting point of a much deeper mystery. For if this knowledge existed to create a rust-proof monument, where else did it appear? And why did such a powerful technology simply fade from the world, leaving behind only silent, enduring witnesses like this one? The pillar in Delhi is a stunning landmark, but it is far from alone. Scattered across the globe, from misty Scandinavian fjords to the islands of Japan, are other metallic echoes of this same ancient ambition. This was not a single, lucky breakthrough. It was a widespread, persistent human dream to master the very essence of metal, to forge something that could defy time itself. Consider the legendary Ulfberht swords, carried by Viking warriors over 1,000 years ago. These were not crude weapons of common iron. Metallurgical studies reveal their blades were made of a steel so pure, with such a high carbon content, that it would have seemed almost magical to contemporaries. The strength and flexibility of this steel, likely imported from far-off furnaces, gave their bearers a terrifying advantage. Across the world, Japanese swordsmiths developed their own sacred art, creating tamahagane steel through a meticulous, weeks-long process of smelting iron sand. The resulting blades, like the famed katana, were renowned not just for their sharpness but for their incredible resilience, a product of precise folding and differential hardening that created a self-repairing molecular structure. Even in ancient China, artisans pioneered the production of cast iron on an industrial scale, creating durable tools and ornate works that survived the centuries. And in the Americas, recent studies of pre-Columbian metalwork hint at sophisticated understanding of alloying and gilding long before European contact. This global tapestry tells a profound story. From the forges of India to the workshops of Europe and Asia, humanity was engaged in a collective, centuries-long experiment. The methods differed wildly, the cultural meanings varied, but the goal was strikingly consistent: to transform a brittle, corruptible ore into something strong, beautiful, and permanent. This diversity is what deepens the mystery. It was not one secret recipe that was lost, but many. Different civilizations working in isolation found different paths to a similar summit. They manipulated carbon content, they experimented with phosphorus and other trace elements, they perfected folding techniques and heat treatments we are still trying to fully decode. The common thread was not a specific formula, but a principle, a relentless drive to push material science to its absolute limit. Why did so many ancient cultures pour such immense resources, such spiritual and artistic devotion, into perfecting metal? The answer lies in what metal represented. It was the edge of a kingdom, the spine of a temple, the heirloom of a family line. To make metal that would not fail was to build a legacy that would not crumble. This shared dream forces us to look past the individual artifact and search for the universal human impulse behind it all. That unique chemical signature is our first tangible clue. When modern spectrometers and electron microscopes finally turned their gaze on artifacts like the Delhi pillar, they did not find a secret coating or some exotic alloy. They found a fingerprint in the iron itself, a deliberate trace of what we now consider an impurity. The iron of the pillar contains about 0.25% phosphorus, a level that would make a modern metallurgist raise an eyebrow. In contemporary steelmaking, phosphorus is viewed as a contaminant. It makes the metal brittle, more likely to crack under stress when worked in large structures or machinery. For this reason, our entire industrial process is designed to remove it, seeking out low phosphorus ores and employing complex refining techniques to purge the element. Yet here, in a 1600-year-old monument, that same impurity is the very reason it still stands. This is the core paradox, an ancient solution that inverts our modern logic. So how does this work? In the right conditions, phosphorus does something remarkable within the iron structure. As the metal cools and interacts with the atmosphere, the phosphorus helps catalyze the formation of an incredibly thin, protective film on the surface. Scientists describe it as a layer of iron-hydrogen phosphate hydrate. That is a complex term for a simple idea, a self-assembling shield. This layer, only a few molecules thick, is dense, stable, and tightly bonded to the metal beneath. It acts as a near-perfect barrier, passively resisting the relentless chemical advances of moisture and oxygen that cause ordinary iron to rust and flake away. It is not a coating applied later like paint or galvanization. It is a skin grown from within, a direct result of the metal's unique internal recipe. This leads us to a critical realization. The ancient smiths could not have known about molecules or phosphates. Theirs was a knowledge written in fire and observation, an empirical mastery gained through generations of trial and error. They learned which specific local ores, when fed into their distinctive furnaces and worked with precise techniques, yielded iron with these extraordinary properties. They were not adding phosphorus as a separate ingredient. They were intuitively selecting and processing ores that already contained it, then managing the smelting and forging process in a way that preserved and utilized its benefits. Whether this was intentional understanding or a happy accident perfected over time is part of the mystery, but the outcome is undeniable. They turned what we call an impurity into the key to immortality for their creations. Their craft accepted the natural character of their materials and worked with it rather than striving to purge it completely. This fundamental difference in philosophy between harnessing an element and eliminating it marks a fork in the road of technological history. But if this knowledge was so powerful, why did we ever choose the other path? The true magic happened not in the ore itself, but in the fire. To understand this lost metallurgy, we must step inside the workshop of an ancient smith, a space filled with heat, smoke, and a profound tactile knowledge. The process began not with a roaring industrial blast furnace, but with a humble yet ingenious device called a Bloomery furnace. Picture a simple clay chimney, often built directly into the earth. Inside, layers of iron ore and charcoal were stacked and set ablaze. A craftsman would tirelessly work bellows, not to create the inferno temperatures of modern industry, but to maintain a precise, relatively low heat over many hours. This was a slow, deliberate dance of chemistry. The burning charcoal produced carbon monoxide, a gas that seeped through the ore, patiently stealing away its oxygen. What remained was not liquid iron, but a spongy, glowing mass mixed with stony waste called slag. This mass was the bloom, a crude but crucial beginning. The smith would then wrest this incandescent lump from the furnace and place it on an anvil. This is where the art truly came to life. With heavy hammers, they would beat the glowing bloom, folding and compressing it with rhythmic, powerful blows. Each strike did more than shape the metal. It forced out the molten slag, welded microscopic iron particles together, and began to align the internal crystalline structure of the material. The smith was not just a laborer, they were a conductor of an unseen symphony, reading the color of the heat from cherry red to brilliant yellow, and listening to the ring of the hammer to understand the metal's condition. This hands-on, intimate process, repeated over and over, created something unique. The slow Bloomery method and the relentless hot working allowed for the formation of a distinctive microstructure. Tiny fibers of iron and subtle slag inclusions were woven together, creating a material that was not perfectly uniform like modern steel, but which possessed a natural, almost fibrous toughness. Crucially, this entire artisanal chain, from selecting the right local ore to managing the furnace atmosphere to the final hammering, preserved and utilized those trace elements like phosphorus. The modern blast furnace, designed for immense speed and volume, operates at such high temperatures that it effectively burns away these subtleties. It produces a flood of homogeneous liquid iron that is then refined to purity, stripping out the very characteristics the ancients harnessed. Their secret may have been this holistic approach, where every step from earth to anvil was part of a single, unbroken ritual aimed at drawing out the hidden potential within the stone. The skill was an unrecorded science, passed from master to apprentice through the heat of the forge and the feel of the hammer. This was the crucible of craft, and when industrialization chose the path of scale and uniformity over this deep, material intimacy, an entire library of tactile knowledge began to fade from the world. But if the method was so effective, why would anyone ever abandon it? The answer lies in a trade-off as old as civilization itself, a choice between quality and quantity that reshaped our world. That microscopic shield is the final, brilliant piece of the puzzle. Rust is not simply the enemy of iron. It is a specific, failed version of a conversation between metal and air. Ordinary rust, what scientists call hydrated iron oxide, forms in a loose, flaky structure. Think of it as a brittle, cracked shell, full of microscopic pores and weaknesses. Once this shell forms, it actually traps moisture against the metal beneath, accelerating its own decay. It is a broken armor that invites the very forces it should repel. The ancient achievement was to guide that chemical conversation toward an entirely different outcome. They fostered the growth of a passivation layer. This is a term that simply means a surface becomes passive or unreactive because it has coated itself in a perfect protective skin. You encounter this phenomenon in everyday life. The green patina on a copper roof is a passivation layer, a stable compound that shields the metal underneath from further corrosion. The dull sheen on an aluminum can is an oxide layer so thin and tough it prevents the rest of the can from oxidizing. The iron pillar of Delhi possesses its own unique version of this genius. Its surface is not bare iron, but a complex, glassy film only about 1/500th of a millimeter thick, a blend of iron, oxygen, hydrogen, and phosphorus. This specific recipe, catalyzed by that deliberate impurity in the metal, creates a barrier that is dense, continuous, and tightly bonded. It is the difference between a suit of armor crafted from a single, flawless plate and one made from a pile of rusted, broken links. The former deflects blows, the latter shatters on impact. The ancient smiths, through their mastery of the entire chain from ore to finished object, learned how to make the metal grow this perfect suit of armor for itself. They controlled the cooling process, perhaps even the immediate atmospheric conditions around the hot metal, to encourage the formation of this stable skin rather than the chaotic scramble of common rust. This was not a coating they applied, it was a quality they evoked from within the material. It is a testament to an engineering philosophy that sought harmony with the natural properties of their world, a dialogue with the elements that resulted in a whisper-thin masterpiece capable of silencing time itself. That whisper-thin shield does not exist in a vacuum. Its survival is a quiet conversation, a lifelong dialogue between the object and the very air it breathes. To understand why the iron pillar still stands, we must look beyond its chemical recipe and into the specific world it has inhabited for centuries. Delhi's climate plays a silent, crucial role. The region experiences a long, intensely dry season with relatively low annual rainfall, punctuated by a fierce monsoon. This cycle, rather than harming the pillar, may have been essential to its preservation. During the dry months, the stable, protective layer on the metal consolidates. Then, when the monsoon rains arrive, they wash away any loose contaminants or salts that might have settled on the surface, effectively cleansing the shield without penetrating it. This specific rhythm of wet and dry allows the passive film to maintain its integrity, a perfect environmental partnership forged by chance or perhaps by deep understanding. But climate alone cannot explain everything. Other artifacts displaying similar resilience have been found in far more demanding environments, from the variable humidity of European churchyards to coastal regions. This suggests the ancient material itself was engineered for a kind of robustness, an inherent ability to find stability even when conditions were less than ideal. This introduces a fascinating concept known as beneficial corrosion. For ordinary iron, all corrosion is destructive, a one-way path to disintegration. But for these specially crafted metals, the initial interaction with the atmosphere was not an attack. It was the first step in building their own defense. A controlled, initial oxidation actually contributed to the formation of that dense, adherent layer. It was as if the metal was designed to greet the elements, to shake hands with the air and moisture, and from that greeting weave its own impermeable cloak. This shifts our entire perspective. The lost knowledge may not have been just a recipe for a static, perfect metal. It could have been an intuitive grasp of environmental synergy. The master smiths were not simply crafting an object, they were crafting a relationship. They may have understood on a practical level how the iron from their particular region worked with their particular techniques, would behave over decades and centuries in their particular climate. They were building for a specific place and a sacred purpose, whether it was a pillar meant to endure under an open sky or a blade meant to withstand the rigors of campaign and sea air. Their craft considered the entire life of the object, anticipating how it would change and settle into the world. This holistic view stands in stark contrast to much of modern industry, which often seeks to create universally uniform materials designed to resist all environments equally, sometimes through energy-intensive coatings that can fail. The ancient approach was one of elegant adaptation, of creating a material that was not just strong, but wise to the world it would inhabit. So if this wisdom was so profound, woven into the very relationship between craft and environment, its disappearance becomes an even greater historical puzzle. What force could possibly sever such a deep-rooted and successful tradition? Across continents and centuries, the dream of an unbreakable blade was etched not just in metal, but in story. Legends speak of swords that could cut through stone, that gleamed without a hint of tarnish, that were passed down through generations as living testaments to their maker's art. Excalibur, drawn from the stone, possessed a purity that symbolized rightful kingship. The Viking hero's sword in the sagas was often his most prized possession, a companion with a name and a lineage as important as its edge. The famed swords of Saladin were said to be so sharp they could slice a floating silk scarf, their steel holding a mirror finish amidst the dust of the desert. For the longest time, we dismissed these accounts as pure myth, the natural exaggeration that comes when a warrior praises his most trusted tool. But what if these stories were not mere fantasy? What if they were the cultural memory, blurred by time and retelling, of a tangible technological reality? They may be the echo of that same lost craft we see in the silent pillar, translated into the language of heroes and epic deeds. The lore of the unbreakable sword likely began with a very real encounter, when a warrior or a king first held a blade forged with that forgotten knowledge. Compared to the brittle, quickly rusting iron of common weapons, this superior steel would have felt miraculous. Its edge would hold through countless clashes. Its surface, developing that stable patina, would resist the red bloom of corrosion that ruined other blades left in their scabbards. In a world where a man's life depended on the integrity of his weapon, such an object would inevitably gather stories. Its durability became invincibility, its longevity became immortality, its maker, a master of a rare and guarded craft, became a wizard or a demigod. The legend was born not from nothing, but from a profound material truth that so outstripped common experience it could only be explained as magic. This bridge from craft to myth becomes strikingly clear when we examine two of history's most celebrated real-world steels. Take the fabled Damascus blades, forged in the Middle East from ingots of Wootz steel imported from India. These swords were renowned for their mesmerizing, watery surface pattern and a terrifying sharpness that folklore claimed could cut a falling hair in two. Modern science, peering at the microstructure of genuine antique examples, found the reason. The steel contained high-purity iron and a specific formation of carbon nanotubes and carbide bands, a nanostructure created through a precise, repeated cycle of heating, forging, and cooling that is still not perfectly replicated today. This gave the blade its legendary edge retention and a subtle, flexible strength. Similarly, the Ulfberht swords of the Vikings, with their inscription inlaid in the blade, were made of crucible steel so pure and free of slag inclusions that they were far more resilient than the softer, more brittle iron weapons of the era. To a Norse raider facing a foe whose sword might snap on his shield, an Ulfberht would indeed seem a gift from the gods. These were not magical items, but they were the pinnacle of material science for their time, so advanced that their capabilities fed directly into the myth-making machine. The stories then served a vital purpose. They were the oral repositories of technical prestige, a way for a culture to remember and venerate an achievement it could not fully explain in technical terms. The line between a superior crystalline structure and a magical property, between a self-healing patina and an enchanted shine, was invisible to the eye. So the knowledge lived on in two forms: the guarded, hands-on craft of the smith and the amplified, celebrated legend of the warrior. When the craft itself eventually faded, victim to shifting trade routes, lost ore sources, or the upheaval of empires, only the legend remained, a ghost of a technology waiting for us to listen closely and hear the truth within the tale. The legendary smith who forged a blade of such quality was more than an artisan, he was a keeper of secrets. This is the human dimension of our mystery, the fragile vessel through which this profound knowledge flowed. In the ancient world, mastery of metal was not contained in textbooks or public patents. It resided in the hands, eyes, and memory of a select few, protected within a system designed for exclusivity. Imagine a workshop shrouded in the smoke of the forge, where a master worked alongside his sons or a handful of sworn apprentices. The knowledge was transmitted not through lectures, but through lived experience, a language of fire color, hammer ring, and the feel of hot metal under the tongs. This was tacit knowledge, understanding so deeply embedded in practice it was difficult, if not impossible, to fully articulate in words. A master might say, "Heat it until the color of a summer sunset," or "Strike when the sound is right." The true meaning of those instructions lived in the thousands of repetitions that came before. This system created incredible masters, but it also built walls around the craft. Guilds and family lineages guarded their techniques with fierce secrecy. Revealing a formula or a unique quenching method could shatter a hard-won trade monopoly, robbing a family of its prestige and livelihood for generations. This secrecy was a rational defense in a pre-industrial economy, but it transformed the craft into a fragile, living library with very few copies. The entire archive of a technological tradition could exist only in the minds and muscle memory of a small, aging group of practitioners. This is where the chain becomes vulnerable. History is rarely gentle. A conflict that swept through a region, a shift in vital trade routes that cut off access to a special ore, or the devastating arrival of widespread illness could erase a lineage in a single generation. The knowledge did not burn in a library fire, it simply faded from living memory as the last masters passed without a suitable heir. The intricate dance of selecting ores, managing furnace atmosphere, and performing the final heat treatment, a process refined over centuries, could vanish into silence because no one was left who remembered the final, crucial steps. The loss was not always a dramatic catastrophe. More often, it was a slow, quiet fading. As economic and social priorities shifted, the demand for such painstakingly crafted, expensive items dwindled. A young person might look at the decades of grueling apprenticeship required and choose a different path. The nuance, the subtle adjustments for different batches of ore, the intuitive fixes for a problematic bloom, these were the first elements to disappear. What might be passed down were the basic steps, but the deep, refined artistry, the true genius of the craft, evaporated. Then came the tidal wave of industrialization, which did not destroy the knowledge through violence, but made it seem obsolete through sheer economics. The new blast furnaces and Bessemer converters prized volume, speed, and standardization above all else. They sought a uniform, predictable product, iron and steel by the ton for railroads, bridges, and machinery. The ancient, artisanal goal of creating a self-preserving, unique material for a specific sacred object was no longer the aim. The new systems were designed to purge impurities like phosphorus, not to harness them. Why spend weeks crafting a single perfect blade when you could produce 100 serviceable ones in a day? The economic logic was overwhelming, and with it, the very mode of knowledge transmission. The hands-on, experiential craft was rendered a quaint relic. The masters did not take their secrets to the grave out of spite, but because the world had fundamentally changed, leaving no one who truly needed to hear them. So the silence grew, punctuated only by the enduring objects themselves, waiting for a future that would learn to ask the right questions. that silent challenge from the past has not gone unanswered. In laboratories around the world, modern scientists have taken up the gauntlet, attempting to reverse engineer a craft that left no written instructions. Their mission is to take the chemical blueprint we have decoded and use it to build a bridge back to the ancient workshop. This is not simply an academic exercise. It is a profound act of technological archaeology, an attempt to resurrect a dialogue with materials that we thought we had mastered. Teams, like those at the Indian Institute of Technology in Kanpur focusing on the Delhi pillar, begin with the known facts. They source iron ores rich in phosphorus, mimicking the likely raw materials of antiquity. They construct small-scale Bloomery furnaces based on archaeological finds, carefully layering ore and charcoal. They monitor temperatures, gas compositions, and cooling rates with a suite of sensors that the original smiths could never have imagined. The goal is to walk, step by controlled step, through the entire ancient process and emerge with a metal that behaves like the original. The results have been both illuminating and humbling. Researchers have indeed succeeded in creating small iron samples with that telltale high phosphorus content. In controlled environments, these lab-grown samples do develop a protective passive layer, demonstrating that the core chemical principle is sound. We can, in a sense, follow the recipe. But the true challenge lies in mastering the art of cooking. The ancient process was not a series of isolated steps, but a continuous, responsive performance. The right slag chemistry was not guaranteed by a formula, but achieved by the smith reading the flow of molten waste from the bloom, judging its color and viscosity. The critical cooling rate that allows the protective film to form was not a preset timer, but a product of the object's final placement, perhaps buried in ash or left in a specific microclimate near the forge. The exact force, angle, and temperature of each hammer blow during hot working align the metal's internal structure in a way that is incredibly difficult to replicate with modern power hammers. A scientific paper can list the percentage of phosphorus, but it cannot convey the precise moment when the metal under the hammer feels right, a knowledge stored in the palms and forearms of a lifetime of practice. This gap between the quantitative recipe and the qualitative craft is where the mystery deepens. Modern analysis can tell us what is in the metal and what is on its surface. It struggles to capture the how, the lived experience of creation. The laboratory can produce a corrosion-resistant sample, but can it forge a 7-ton pillar? Can it create a blade that sings through the air and holds an edge through conflict? The scientific efforts, while groundbreaking, ultimately serve as a powerful testament to the sophistication they seek to copy. They highlight that the lost knowledge was a seamless fusion of material science, environmental intuition, and embodied skill. Each successful, small-scale replication is a victory, but it is also a quiet reminder of the vast, unrecorded wisdom that resided not in a book, but in the rhythm of the forge and the watchful eye of the master. We are learning to read the words of this ancient language, but we are still deciphering the poetry. This presents a fascinating contradiction at the heart of materials science. In our modern industrial world, phosphorus in steel is a problem to be solved. Metallurgists refer to it as a cause of cold shortness, a term that describes steel becoming dangerously brittle at normal temperatures. It loses its ability to bend or flex, instead snapping suddenly under stress or impact. For building skyscrapers, bridges, or any structure bearing dynamic loads, this is an unacceptable flaw. Our entire production chain, therefore, is engineered to remove phosphorus, seeking purity as the ultimate goal. Yet the iron pillar of Delhi, and likely other ancient artifacts, flips this logic completely. Its iron is not pure by our standards, it is deliberately impure, and that very impurity granted it immortality. So how did these objects not shatter like glass? How did ancient smiths overcome the cold shortness that defines phosphorus for us today? The answer may lie not in eliminating the element, but in mastering its behavior through the entire craft. One compelling theory focuses on the unique internal world of the ancient metal. Under the microscope, this iron is not a uniform, homogeneous block. It is a composite material, a landscape woven with fine, thread-like inclusions of slag, the glassy waste product from the smelting process. These slag stringers are not flaws, they may be a key feature. Some researchers suggest they could act like microscopic reinforcement bars, subtly diverting and stopping the propagation of cracks that phosphorus-induced brittleness might start. The phosphorus itself might not be evenly distributed, but locked away in forms or locations within this complex microstructure that minimize its harmful effects on toughness. Another simple, practical answer is one of application. The pillar is a monument. It stands vertical, bearing mostly its own immense weight in compression. It was never designed to be a spring, a blade, or a structural beam experiencing sudden shocks. The ancient artisans chose this specific material recipe for a specific purpose: monumental stability. They traded away tensile flexibility, a property the pillar would never need, for the supreme gift of corrosion resistance. In doing so, they executed a brilliant piece of material engineering, matching the property to the purpose with perfect precision. There is also the possibility of lost techniques, perhaps through specific sequences of heating and hammering, or through controlled cooling methods now forgotten. The smiths learned to manage the brittleness, to align the crystalline structure in a way that accommodated the phosphorus. Their craft was an entire system where the choice of ore, the furnace conditions, the forging ritual, and the final use were all parts of a single equation. They were not fighting the impurity, they were collaborating with it, directing its influence toward a singular, magnificent outcome. This forces a profound shift in perspective. It challenges our modern reverence for purity and uniformity. In our quest to create the perfect blank slate material, we may have discarded pathways that the ancients explored, pathways where strategic impurities were not contaminants but collaborators. Their definition of a perfect material was not one free of all other elements, but one where every element present was guided to play a beneficial role. The phosphorus paradox is not just a metallurgical curiosity, it is a lesson in design philosophy, asking us whether true strength always comes from purity, or if it can sometimes emerge from a wise and intentional embrace of complexity. The silent testimony of these ancient metals requires a new kind of listening. This is where archaeometallurgy enters the story, a field that acts as a translator between the past and the present. It is a fusion of archaeology and materials science, a detective agency where the clues are measured in microns and the witnesses are atoms. When a tiny, carefully extracted sample from an artifact like the Delhi pillar arrives in the lab, it is not destroyed but invited to tell its full story. Researchers employ a suite of advanced tools to listen. A scanning electron microscope, or SEM, acts as an incredibly powerful eye, scanning the sample with a focused beam of electrons to create a highly detailed, three-dimensional image of its surface at magnifications thousands of times beyond what any ancient smith could have seen. They can see the microscopic topography of the protective patina, or peer at the fractured edge of the metal to examine its internal world. X-ray diffraction, or XRD, is another key instrument. It bombards the sample with X-rays and analyzes the pattern in which they scatter. Every crystalline substance scatters X-rays in a unique way, like a fingerprint. This allows scientists to identify the exact minerals and compounds present, whether it is the specific iron phosphates in the passive layer or the different forms of slag trapped within the metal. But perhaps the most revealing technique is metallography. Here, a small sample is mounted in resin, polished to a mirror finish, and then etched with a mild acid. This process highlights the metal's microstructure, making visible features that are utterly hidden to the naked eye. Under the microscope, a history written in crystal unfolds. The size and shape of the iron grains reveal the object's thermal biography. Large grains suggest it was heated to high temperatures and cooled slowly, while small, fine grains indicate rapid cooling or extensive mechanical working like hammering. The patterns of these grains can show where the metal was folded, how many times it was worked, and even the direction of the final hammer blows. Slag inclusions, those tiny stringers of glassy waste, are not just imperfections. Their composition, shape, and distribution tell a story about the original ore, the temperature of the smelting furnace, and how skillfully the smith worked the bloom to squeeze them out. Even the products of corrosion, the rust itself, are read as a narrative. The layered structure of corrosion products can chronicle centuries of environmental exposure, like the rings of a tree. This forensic scrutiny transforms an artifact from a static object into a frozen moment of ancient practice. It allows us to virtually step into the workshop and watch over the smith's shoulder. We can see the evidence of a critical quench in water, a final annealing heat treatment, or a repair made centuries later. This scientific rigor is what turns vague historical claims and legendary descriptions into verifiable, concrete data. It is how we move from saying the metal is special to understanding, atom by atom, precisely why. This meticulous reading of history through a microscope is our most powerful tool for reassembling the fragmented recipe of a lost world, giving voice to the silent wisdom locked inside the iron. Far to the southeast of Delhi, another monument whispers a similar secret. Rising from the coastal plains of Odisha, the Konark Sun Temple stands as a 13th-century poem carved in stone, dedicated to the sun god Surya. Its design is a monumental chariot with 24 intricately carved stone wheels pulled by 7 stone horses, a breathtaking feat of architecture. Yet woven into this sandstone masterpiece was another, less visible marvel: iron. Massive iron beams, some reportedly over 30 feet long, were used as structural supports within the temple's towering sanctuary. These were not mere pins or brackets, but the hidden skeleton of the sacred space, holding tons of stone aloft in the humid, salt-laden air just a few miles from the Bay of Bengal. This coastal environment presents a corrosion challenge far more aggressive than Delhi's dry interior, where salt spray accelerates the decay of ordinary metal at a frightening pace. And yet, for centuries, historical accounts and local tradition maintained that these iron components endured with little sign of the red decay one would expect. They became part of the temple's legend, a hidden strength within the stone. While many of these beams have since been removed, lost, or have succumbed to time, their story provides a critical second chapter in our investigation. It shows this lost craft was not confined to a single place, time, or environment. The artisans of Konark, working 400 years after the Delhi pillar's creation, faced a different problem. They needed a metal that could provide immense tensile strength in a hidden, structural role while resisting an atmosphere saturated with corrosive sea salts. They likely sourced their iron from different local ores, rich in the mineral laterite, which would have its own unique chemical signature. Their techniques, passed down through generations but adapted to their specific needs, may have varied in the details of forging or finishing. The goal, however, was the same: to create a material in harmony with its duty and its environment. The fact that these beams gained a reputation for longevity suggests they succeeded, at least for a remarkable span of time. This case study shatters the idea of a single, static secret formula. Instead, it paints a picture of a living, adaptable technological tradition. The core principles, understanding how trace elements in local ores could be guided to form a protective alliance within the metal, remained constant. But the application was fluid. tailored to whether the final creation was a freestanding pillar under an open sky or a hidden beam in a humid coastal temple. This adaptability makes the knowledge's disappearance even more poignant. It was not a rigid recipe that could be easily lost, but a sophisticated, systemic understanding of materials that could evolve with circumstance. The Konark beams, whether still partly intact or now only a memory in historical texts, stand as a testament to that flexibility. They deepen the mystery not by providing a simple answer, but by proving the ancient craft was far more widespread and intellectually robust than we ever assumed. If the knowledge could thrive from the dry plains of Delhi to the salty coast of Odisha, solving different engineering puzzles across 800 years, its eventual silence across the entire subcontinent speaks to a collapse not of a technique, but of an entire ecosystem of wisdom. The pursuit of perfection is never just a technical goal. It is a mirror held up to a culture's deepest priorities, reflecting what it considers sacred, valuable, and worth preserving for eternity. To understand why ancient societies invested generations of knowledge into rust-proof iron, we must look past the forge and into the heart of their world. For a king commissioning a monumental pillar, the motivation transcended mere construction. This was an act of spiritual and political alchemy. A pillar that touched the sky and never crumbled was not just a marker, it was a permanent testament to divine favor and unshakable royal authority. It declared to both subjects and rivals that this rule, like the metal itself, was ordained to endure. The incredible investment of resources and elite artisan skill was justified by a value system that placed supreme importance on legacy, on creating symbols that would outlast dynasties and speak to gods and ancestors across millennia. In this context, the slow, meticulous craft was not inefficient. It was the only path to achieving a cosmic level of permanence. The calculus shifted for the realm of weaponry, but the underlying drive for material perfection remained equally intense. For a warrior, a superior sword was not merely a tool, it was a lifeline. Its durability directly translated to survival on the battlefield, where a broken blade meant a lost life. Beyond survival, such a weapon carried immense prestige. A named sword, known for its unfailing edge and uncorrupted beauty, became a hero's identity, a treasure that could elevate a family's status for generations. This created a powerful economic engine. Master smiths who could produce these legendary blades commanded fortunes, and their works became coveted trade goods, circulating across continents and cultures. The value placed on such objects made the painstaking, weeks-long process of folding, forging, and tempering a sound economic decision. The market rewarded the unique, the durable, the transcendent. Craftsmanship was synonymous with value, and time invested in creation was seen as an investment in everlasting worth. Contrast this with the values that ignited the Industrial Revolution and ultimately eclipsed these ancient traditions. The new paradigm was not permanence but productivity, not uniqueness but uniformity. The driving forces became speed, cost efficiency, and replaceability. The goal was to produce not one perfect sword for a king, but 10,000 reliable rails for a railroad, not a single eternal pillar, but abundant, affordable girders for burgeoning cities. This shift was revolutionary, lifting millions from hardship and building the modern world. But it also fundamentally redefined our relationship with material goods. In an economy built on scale and growth, an object designed to last 1,000 years became a kind of economic paradox. Why make something that never needs replacing when your entire system depends on continuous production and consumption? This may be the most profound clue to the technology's disappearance. The loss was likely not a sudden forgetting, but a slow fading of relevance. As societal values pivoted from permanence to progress measured in output, the meticulous, time-intensive craft of making self-preserving metal ceased to be a priority. The knowledge depended on a cultural ecosystem that revered the durable masterpiece, an ecosystem that industrialization quietly dismantled. The masters did not lose the secret, the world simply stopped asking for it. The ancient pursuit, then, reveals itself as something far richer than a clever chemical trick. It was a material expression of an ideology, a belief that the finest human creations should aspire to the timelessness of the mountains and the stars. In our age of disposable plenty, their silent, rust-proof monuments ask us a quiet question about the true cost of convenience and what we might have sacrificed in our race to build a world that moves faster, but perhaps forgets how to endure. That different philosophy becomes strikingly clear when we compare their approach to our own. Today, our battle against rust is fought primarily on the surface. We have developed ingenious, often highly effective methods, but they share a common strategy, applying a protective barrier from the outside in. Galvanization, for instance, involves coating steel in a thin layer of zinc. This zinc sacrificially corrodes first, slowly giving itself up to protect the underlying iron. It is a brilliant guardian, but a disposable one. Once the zinc layer is fully consumed or scratched through, the steel beneath is exposed and vulnerable. Stainless steel takes a different route, alloying the iron with a significant amount of chromium. This chromium, like the phosphorus in the ancient pillar, helps form a passive oxide layer. Yet this modern layer is typically just a few atoms thick and can be compromised in certain harsh environments, leading to pitting or crevice corrosion. Then there are the most common solutions of all, paints and polymer coatings. These create a physical shield, a wall between the metal and the elements. Their success depends entirely on the integrity of that wall. A single chip, scratch, or manufacturing flaw can become a gateway for decay to begin its work from beneath the surface. All these methods are additive. They involve taking a mass-produced, standardized metal and giving it a protective skin in a secondary, often energy-intensive process. The ancient method turned this logic inside out. Their protection was not added on, it was grown out. It emerged from the very bulk of the material as a direct result of its internal chemistry and the craft of its making. The passive layer was not a separate coating. It was the metal's own transformed surface, an integral part of its being. This distinction reveals a fundamental difference in design philosophy. Our modern solutions excel in versatility and scalability. We can galvanize a mile of guardrail or manufacture stainless steel appliances by the million. These processes are engineered for the global market, creating materials that perform predictably in a wide range of conditions. But they often create a system with a single point of failure, the integrity of the coating. The ancient approach traded that versatility for a deep, holistic resilience. By engineering the entire volume of the metal to participate in its own defense, they created a form of protection that was inherently self-renewing at a microscopic level. If the surface film was slightly damaged, the underlying metal, with its same chemical predisposition, could reform a protective layer in the right conditions. It was not a shield that could be stripped away, it was a property of the substance itself. Of course, this came with significant trade-offs. The ancient craft was intensely laborious, demanding the full attention of a master smith for weeks or months to produce a single object. It was also deeply material-specific, relying on particular local ores with the right trace elements and a craft tradition finely tuned to those materials. You could not simply apply this technique to any lump of iron ore from anywhere in the world. This comparison does not cast one method as superior to the other. Instead, it reframes the ancient technique not as a primitive precursor, but as a parallel, highly sophisticated branch on the tree of materials science. They achieved a similar goal, corrosion resistance, through a radically different path, one that sought longevity through harmony with the material's intrinsic nature rather than through external control. Their success asks us to consider whether our relentless pursuit of universal, scalable solutions has caused us to overlook elegant, localized strategies where durability is woven into the very fabric of the object from its first moment of creation. Was it brilliant design or a fortunate accident? This question lies at the heart of the scholarly debate surrounding this lost metallurgy, forcing us to consider how innovation truly unfolds in the absence of written theory. On one side, proponents of the accidental discovery theory paint a compelling picture of gradual, unconscious mastery. They point to the fundamental role of geography. Ancient smiths were not global importers. They used the ores available in their immediate region. Certain areas, like the ancient iron mines of India, are naturally rich in phosphorus-bearing minerals. If a community's traditional smelting and forging methods, passed down unchanged for generations, happen to process these specific ores in a particular way, the beneficial rust-proofing effect would emerge consistently, yet invisibly. The smiths would know that iron from this hill, worked in our family's way, produces metal that stands proud against the rain. They would not need to understand phosphorus, only the reliable outcome of a trusted process. The consistency, then, is not proof of deep understanding, but of a stable tradition interacting with a stable local resource. The results were a happy, repeated coincidence, their cause as mysterious as the changing seasons. The opposing view, the deliberate design theory, finds this explanation insufficient. Its advocates look at the sheer sophistication of the results, from the Delhi pillar to the legendary blades, and see the fingerprints of intentional control. They argue that such consistent, high-level outcomes across centuries and vast distances could not be mere repeated luck. The artisans they propose were masterful empirical scientists. Through relentless observation and experimentation over generations, they learned to manipulate variables they could perceive. They would have noted that ore from one particular deposit, when smelted with charcoal of a certain density and worked at a precise heat, yielded a superior metal. They learned to read the clues, the color of the flame, the behavior of the slag, the ring of the hammer on the anvil. This accumulated practical wisdom allowed them to intentionally reproduce the conditions for success, even if they explained it in terms of ritual, divine favor, or the spirit of the metal. For them, the knowledge was not chemical but causal, a deep understanding that action A under condition B yields result C. The most likely truth, as is often the case with ancient technology, is an elegant blend of both. It probably began with an accidental discovery. Someone, somewhere, noticed that metal from a certain ore behaved differently, resisting the red bloom that claimed other iron. This observation did not fade, it was remembered. The next generation, and the one after that, would seek to replicate and refine that outcome. Through a slow, centuries-long process of trial, error, and keen observation, the accidental gift was shaped into a repeatable craft. The underlying principles of phosphorus content and passive layer formation remained a mystery, but the practical steps to achieve them became a guarded tradition. This is how many great technologies of the ancient world evolved, rigorous practice racing far ahead of formal science. The builders of the Roman aqueducts did not need fluid dynamics equations to understand gravity and hydraulic grade lines. They observed water's behavior and perfected their engineering through monumental practice. Similarly, the master smiths built a cathedral of practical knowledge, brick by brick, over generations, creating a technology that was both discovered and designed, a testament to the human capacity to master the world through patient, watchful hands. Perhaps the deepest inspiration was not found in other workshops, but in the world outside the forge. Long before the word biomimicry entered our vocabulary, ancient innovators were master observers of nature's engineering. They lived in a world where the most durable structures were not built by human hands, but grew from the earth or were formed by life itself. A master smith, contemplating how to make metal endure, might have looked to the seashore. There, waves crash endlessly against seashells, yet the shells persist. Their strength does not come from a single, pure substance, but from a clever composite of calcium carbonate and organic proteins, layered in a way that deflects force and resists fracture. He might have studied the bones of animals, lightweight yet incredibly strong, another composite of mineral and fiber. Even the landscape offered clues. Certain stones and outcrops developed a hard, stable patina after centuries of exposure, a kind of stone skin that protected the softer rock beneath. While we have no written record stating a smith copied a seashell, the philosophical connection is profound. These natural models taught a universal lesson. Durability often arises from complex, layered structures and from forming a cooperative relationship with the environment, not from resisting it utterly. This aligns perfectly with the ancient metallurgical achievement. They did not seek to prevent the natural process of oxidation, they learned to guide it. They worked with it, coaxing the metal to form its own stable, protective skin, much like a pearl forms around an irritant or a callus forms on skin. This was a nuanced, almost ecological approach to materials. It viewed the metal not as an inert substance to be dominated, but as a participant in a dynamic process, one that could be directed toward a state of graceful equilibrium. This perspective ties the technological mystery to a broader ancient worldview. In many traditional systems of thought, human craft was not seen as separate from nature, but as an extension of its principles. The potter's wheel echoed the turning of celestial bodies, the weaver's loom mirrored the patterns of vines and rivers, and the smith's forge harnessed the transformative power of the mountain's heart. To create something lasting, one had to align with these deeper rhythms, to integrate rather than conquer. The rust-proof iron stands as a perfect symbol of this philosophy. It achieved immortality not by defying the natural tendency of iron to interact with air, but by collaborating with that tendency to reach a higher state of stability. It represents a form of wisdom where the goal was harmony, a seamless joining of human intention with the inherent logic of the material world. In our modern quest for control, have we forgotten how to listen for that kind of logic? The quiet fading of a craft can be the echo of a much louder historical rupture. The gradual disappearance of this metallurgical wisdom did not occur in a vacuum, but was accelerated by the immense pressures of colonialism and the relentless tide of industrial standardization. As European powers expanded their reach across the globe, they brought with them not just new rulers, but an entirely new economic logic. Colonial economies were often engineered to extract raw materials and create markets for finished goods from the colonizing nation. This system had a devastating effect on local artisan networks. The intricate, high-value craft of the master smith, producing unique blades or architectural elements for local elites and temples, was suddenly competing with cheaper, mass-produced iron and steel goods shipped from factories thousands of miles away. The cultural and spiritual value embedded in a hand-forged object held little weight in a ledger focused on volume and cost. The specialist smith, once a revered figure, found his work economically devalued, his patrons displaced, and the demand for his supreme artistry dwindling in the face of convenient, imported alternatives. Furthermore, colonial administrations frequently established large-scale, European-style ironworks within their territories. These facilities were designed for bulk production, using familiar Western methods to process local ores into standardized forms for construction and export. They employed new workforces trained in these foreign techniques, deliberately sidelining the traditional smiths whose nuanced, experience-based methods were seen as archaic, inefficient, and incompatible with the goals of rapid resource extraction. The knowledge was not stolen, it was simply made irrelevant by a new system that had no use for its subtlety. This marginalization was then cemented by the global industrial paradigm of the 19th and 20th centuries. The New Age worshipped scalability, uniformity, and documented process. Factories required blueprints, precise chemical formulas, and repeatable procedures that could be taught quickly to any worker. The genius of the ancient craft resided in the opposite realm, in tacit knowledge. It lived in the smith's ability to judge a heat by the color of the flame, to adjust his hammer strikes by the sound of the metal, to feel the right moment in a process that had never been written down. This kind of embodied skill was invisible to the engineers of the New World. It could not be easily translated into a manual, patented, or integrated into an assembly line. In the relentless push for progress measured in output per hour, such deeply personal, time-intensive mastery was not just overlooked, it was systematically rendered obsolete. The loss, therefore, was more than a forgetting. It was an active superseding, a whole way of knowing, a philosophy of working in harmony with local materials to achieve a specific, profound form of permanence, was swept aside by a paradigm that prioritized different values, speed, volume, and universal application. The old masters did not fail to pass on their secrets. The world around them changed so fundamentally that there was no longer a place for the language in which those secrets were spoken. Their silence is a monument to a different kind of fracture, one where the very metrics of what constitutes progress were rewritten, leaving certain forms of human genius to fade into the landscape like forgotten inscriptions on a rust-proof pillar. True revival demands more than a laboratory recipe. To bring this ancient craft back to life, we must step out of the clean, controlled lab and into the unpredictable reality of the workshop, confronting a series of practical hurdles that separate theory from tangible metal. The first challenge is the very earth itself. Modern steel mills prize uniformity, sourcing iron ore from massive, homogenized deposits. To recreate the ancient method, researchers and artisans must first locate and identify specific ores rich in the necessary trace elements like phosphorus, but free of harmful ones like excessive sulfur. This often means seeking out small, forgotten deposits or even analyzing historical slag heaps to reverse engineer what the original smiths were using. It is a form of geological detective work, a search for the right raw clay before the sculpture can even begin. Then comes the furnace. Constructing and operating an authentic bloomery is an art in itself. The right clay mixture for the liner must be gathered, prepared, and shaped to withstand intense heat, while also influencing the furnace's internal chemistry. The bellows, whether hand-pumped or recreated with modern equivalents, must provide a consistent, gentle airflow, not the roaring blast of industry. Managing this fire is a constant physical dialogue, requiring the operator to read the color of the smoke, listen to the sound of the burn, and make minute adjustments over many hours to nurture the slow reduction of ore into a metallic bloom. Finally, there is the moment of truth, the forging. When the incandescent bloom is hauled from the furnace, the real test of embodied skill begins. This is not a uniform billet of modern steel. It is a heterogeneous, spongy mass of iron and slag, glowing with potential and fragility. Mastering the hammerwork to consolidate this mass, to weld it into a solid bar while working at precisely the right temperature, requires an intuitive touch that no textbook can impart. It is knowledge stored in the muscles and the senses, in the feel of the hammer's rebound and the visual cues of the metal's color as it cools. Across the globe, experimental archaeologists and dedicated artisan blacksmiths have taken on this profound challenge. Their projects are not about producing a useful product for sale, but about conducting a live interview with the past. In these reconstructions, every variable becomes a teacher. The type of clay in the furnace liner might subtly alter the slag chemistry, affecting the final metal's purity. A slight change in the rhythm of hammering can mean the difference between a coherent bar and a crumbling mass. One team might succeed in creating a small, corrosion-resistant sample, while another, following what seems to be the same steps, produces a brittle, useless lump. Each failure is as instructive as a success, revealing another layer of nuance that pure chemical analysis could never predict. these modern pioneers are slowly mapping the contours of a lost landscape. They are discovering that the ancient craft was not a linear set of instructions, but a holistic ecosystem of knowledge. It integrated geology, pyrotechnology, and physical artistry into a single, seamless practice. The true challenge of revival, then, is not merely to replicate a chemical composition, but to resurrect this entire way of thinking and working with the material world, a system where every element, from the clay of the earth to the swing of the arm, played an essential part in whispering immortality into iron. This forgotten craft could speak directly to our most pressing modern dilemmas. Imagine the potential if we could integrate its principles with contemporary engineering. Coastal cities and offshore structures face a relentless war against saltwater corrosion, a battle fought with constant maintenance, toxic antifouling paints, and frequent replacement. What if, instead, we could design the foundational supports themselves from a material engineered to form a stable alliance with that harsh environment? The ancient approach suggests a path toward ultra-durable marine components, from bridge pilings to tidal energy installations that require far less chemical intervention and generate less waste over their vastly extended lifespans. Similarly, in infrastructure, the dream of bridges or railways that need repainting only once a century, not once a decade, moves from fantasy into the realm of material science possibility. This would not mean copying a 1,000-year-old recipe verbatim, but learning from its core philosophy to design metals that participate in their own preservation from the inside out, reducing our reliance on external, often environmentally costly protective systems. Beyond specific applications, the ancient method offers a profound lesson in sustainability viewed through a different lens. The entire process was inherently low energy and localized. The furnace was heated by renewable charcoal from managed woodlands. The ore was sourced from nearby deposits, minimizing transport. The energy input was human skill and time, not the colossal fossil fuel consumption of a modern blast furnace. Most importantly, the product was designed for extreme longevity. This creates a radically different material economy. Instead of a high-throughput system that produces disposable goods with planned obsolescence, this was a slow technology model where immense value was placed on creating an heirloom object, something built to last for generations. The resource and energy cost was front-loaded into a single, magnificent act of creation meant to echo across centuries. This stands in direct opposition to our current culture of disposable plenty, where the environmental cost of constant production and replacement is often hidden. The true relevance for our future may not lie in abandoning modern industry, but in seeking a synthesis. Can we marry the efficiency and scalability of contemporary manufacturing with this ancient reverence for durability and material harmony? This integration could inspire a new materials philosophy. It would shift our primary design goal from lowest upfront cost to longest functional life and lowest total environmental impact over decades or centuries. It asks us to reconsider our relationship with the things we build, valuing stewardship over consumption. In an era defined by climate challenges and resource constraints, the silent testimony of a rust-proof pillar is no longer just a historical curiosity. It becomes a compelling prototype for a different way of being in the world, one where we build not just for our time, but for time itself, creating a legacy of resilience woven directly into the fabric of our civilization. The truth about these ancient metals is often more impressive than the myth. A common misunderstanding is that artifacts like the Delhi pillar are completely immune to corrosion, that they exist in a state of perfect, unchanging purity. This is not the case. The correct term is extraordinary corrosion resistance. The metal developed a stable, protective patina, a kind of graceful aging that halts the destructive process of rust. It is not a shield against time, but a profound negotiation with it, achieving a state of equilibrium where decay is effectively paused. This distinction is crucial because it moves us from a fantasy of invincibility to the reality of a brilliant material science achievement. The ancients did not conquer nature's laws, they learned to work within them to achieve a lasting peace. Another popular idea is that there was a single, universal secret formula, a lost recipe that, if found, would unlock everything. The evidence tells a different story. From the phosphorus-rich irons of India to the carbon-controlled steels of Viking swords and the complex folding techniques of Japan, we see a range of solutions. This was not one secret but many, different cultures using different local ores and facing different environmental challenges developed their own specialized pathways to a similar goal: long-term durability. This regional adaptation makes the phenomenon not less remarkable, but more so. It reveals a widespread, deep-seated human drive to solve the problem of decay, a drive that manifested in wonderfully diverse forms of technical creativity. We must also be careful not to view this ancient knowledge through a lens of simplistic superiority. It represented a peak of specialization. These metallurgists mastered the art of creating a material supremely resistant to one specific threat: long-term atmospheric corrosion. This came with inherent trade-offs. The high-phosphorus iron of the Delhi pillar, for instance, would likely be too brittle for use in a modern bridge or the frame of a moving vehicle, where flexibility and shock resistance are paramount. Their craft was also incredibly labor-intensive and difficult to scale, the antithesis of modern mass production. It excelled in creating singular, heirloom-quality objects meant to endure in a specific role, not in producing versatile, uniform materials for a globalized world. Appreciating this nuance allows us to honor their achievement without diminishing our own. Finally, it is vital to remember that not all ancient iron possesses this property. The vast majority of historical iron artifacts show the expected signs of corrosion and decay. The rust-proof examples we study are the rare exceptions, the masterpieces that represent the absolute pinnacle of the craft. They were the product of elite knowledge, access to specific resources, and a cultural context that valued such an investment. This separates the technological marvel from mere antiquity. It underscores that what we are examining is not the standard practice of the ancient world, but its highest art, a specialized achievement that stood far above the commonplace. By setting the record straight on these points, we strip away romanticized distortion. In its place, we find a clearer, more respectful view of a genuine sophistication. We see ancient metallurgists not as magicians possessing lost super science, but as brilliant empirical engineers who optimized their materials for a sacred purpose, achieving a form of longevity that still commands our awe and our rigorous study. Their true legacy lies in this nuanced material conversation with eternity. The investigation now enters a new dimension, one measured in laser points and virtual simulations. Digital archaeology is providing a powerful new lens, allowing us to examine these ancient metals without ever touching their surfaces. Teams of researchers begin by encircling an artifact like the Delhi pillar with a constellation of high-resolution scanners. Lasers sweep across its form, capturing millions of precise data points that define every contour, every subtle undulation, and even the microscopic texture of its legendary patina. This process creates a perfect digital twin, a three-dimensional model so accurate it can be studied, measured, and shared with experts across the globe, all while the original monument remains undisturbed in its centuries-old vigil. This is more than just a preservation tool, it is a new form of perception. By mapping the micro-topography of the protective layer, scientists can analyze its uniformity, study how it has weathered over time, and identify any areas where environmental stress might have caused subtle changes invisible to the human eye. The digital model becomes a permanent, interrogatable record of the artifact's current state, a baseline against which future change can be measured with nanometer precision. But the digital tools go far beyond static replication. Computational modeling takes the chemical data we have and sets it into motion. Researchers can feed variables into sophisticated programs, ancient alloy composition, local humidity cycles, temperature ranges, even atmospheric pollution levels from different eras. The software then runs simulations, projecting how the corrosion process might unfold over decades, centuries, or millennia under those specific conditions. We can ask the model questions. What if the pillar had been erected in a coastal environment? How would a different phosphorus concentration have altered the formation of its protective skin? These virtual experiments allow us to test hypotheses about the technology's resilience and its limits, exploring scenarios that would be impossible to recreate in the physical world. Perhaps most transformative is the power of digital correlation. For the first time, detailed scan data, metallurgical analyses, and historical records from artifacts scattered across continents can be united in a single, searchable digital archive. A researcher in Europe can instantly compare the crystalline structure of a Viking sword with the elemental profile of a temple beam from India. Advanced algorithms can sift through this vast, interconnected dataset, searching for hidden patterns, common material signatures, or shared technical solutions that would remain invisible to a scholar studying any single object in isolation. This digital lens allows us to zoom from the atomic arrangement of the passivation layer all the way out to a global map of technological kinship. We are no longer just studying individual masterpieces. We are beginning to trace the faint, fragmented outlines of an entire intellectual tradition, connecting dots across time and space to see a picture that has been lost for 1,000 years. This is the promise of the new digital archaeology, not to replace the physical study of these wonders, but to surround them with a constellation of data, helping us listen more closely to the quiet story they have been waiting to tell. This silent dialogue between smith and metal reveals a deeper truth about knowledge itself. The mastery that created rust-proof iron was not a collection of facts, it was a living intelligence woven into the very body of the craftsman. This is what scholars call embodied knowledge, understanding that resides not in books, but in the hands that judge a heat by its color, in the ears that discern the ring of the hammer, and in the instincts that feel the right moment within the rhythm of the forge. It was a continuous physical conversation, a three-way dialogue between the artisan, the glowing material, and the capricious fire. Each variable was sensed, not measured. The correct temperature was not a number on a gauge, but the specific shade of orange in the heart of the coals. The metal's readiness was a sound, a particular resonance as the hammer struck. This form of intelligence is profoundly difficult to translate into written instructions. You cannot fully capture in a manual the precise pressure of a thumb testing the slag's flow, or the subtle weight shift a master uses to guide a hammer blow for maximum effect. This knowledge was learned through a lifetime of repetition and mentorship, passed from teacher to apprentice in the shared heat of the workshop, through demonstration, correction, and silent observation. Its disappearance, then, is more than the loss of a technique. It is a stark reminder of the historical fragility of non-textual knowledge systems. When a lineage of masters was broken by conflict, by shifting economies, or by the simple passage of time without a suitable heir, an entire library of wisdom could vanish in a single generation. The library was not on shelves, it was in the muscles and memories of human beings. This is why modern attempts at revival face such a profound challenge. Recovering this craft is not merely about reverse engineering a chemical formula, which we can now do in a lab. It is about attempting to recover a different way of being in the world, a different mode of understanding. It asks us to appreciate a form of intelligence that seamlessly integrated acute sensory perception, the ritual discipline of practice, and a deep, almost intimate familiarity with the behavior of natural materials. The master smith did not see ore as a raw commodity, but as a partner with its own character and potential. His work was a negotiation, a coaxing of latent properties into being through disciplined action. From this perspective, the ancient smith transcends the role of a simple technician. He becomes a philosopher of matter, a practitioner who engaged with the fundamental questions of transformation and permanence through the direct physical medium of his craft. His forge was a classroom, his anvil a laboratory, and his finished pillar or blade was a thesis written in enduring metal, a statement about humanity's desire to collaborate with the natural world to create something that whispers across the centuries. The master smith's intuition and the scientist's spectrometer speak different languages, yet they are telling the same story. To reassemble a lost technology, we cannot rely on a single voice. The full picture only emerges where these voices converge, in a space where history, science, and craft meet in a shared conversation. This is the power of interdisciplinary synthesis, a collaborative model that is revolutionizing our understanding of the ancient world. It begins with the historian who sifts through faded inscriptions and chronicles, not just for mentions of metal, but for clues about its value, its trade routes, and the social status of those who made it. They provide the narrative, the cultural vessel that held this knowledge. The archaeologist then maps the physical world of that knowledge, excavating the remains of furnaces, analyzing slag heaps, and recovering the very tools, the hammers and tires, that were extensions of the smith's own hands. These material traces give us the workshop floor, the stage upon which the craft was performed. But to understand the performance itself, we need the materials scientist. Armed with electron microscopes and X-ray diffractometers, they peer into the atomic heart of an artifact. They translate the silent, microscopic evidence into data, identifying the precise crystalline structures and chemical bonds that confer that legendary durability. They provide the what and the how at a fundamental level, yet data alone cannot capture the dance. This is where the modern craftsperson enters, the experimental archaeologist or artisan blacksmith who takes this gathered information and attempts to breathe life back into it. They build a replica furnace based on archaeological plans, source ore from a similar geological deposit, and step into the fire and smoke with their own hands. Their work is a form of physical interrogation, a test of whether our theoretical understanding can withstand the unpredictable reality of flame, draft, and the stubborn character of hot iron. The true breakthrough occurs in the feedback loop between these disciplines. A scientist's finding about phosphorus distribution prompts a smith to adjust their forging temperature. A blacksmith's difficulty in consolidating a bloom sends an archaeologist back to re-examine the tool marks on an ancient anvil. A historian's discovery of a trade record about ore shipments gives the whole team a new geographical clue to pursue. No single field holds the monopoly on truth. The complete answer is woven from their combined threads. This collaborative model actively breaks down the traditional silos of academia, granting equal respect to theoretical analysis and practical, hands-on experiment. It acknowledges that the knowledge we seek was itself holistic, blending empirical observation, material intimacy, and cultural meaning into a single, seamless practice. In this way, the century-spanning mystery of rust-proof iron becomes far more than a historical puzzle. It transforms into a living blueprint for how we might investigate other lost technologies, from the concrete of the Romans to the legendary flexible glass of ancient lore. It demonstrates that the most profound secrets of the past are not locked away in a single scroll or a lone laboratory result. They are dispersed, waiting to be patiently reassembled through a respectful synthesis of every way humanity has ever sought to understand the world, through story, through excavation, through measurement, and through the enduring wisdom of the human hand. This pursuit of lost knowledge is not without its profound ethical complexities. As our tools for investigation grow more powerful, so too does our responsibility to the irreplaceable objects and the living cultures they represent. Take the Iron Pillar of Delhi itself. It is a national treasure, a sacred monument, and a fragile witness to 16 centuries of history. The question becomes, how far should we go in our quest to understand it? Should researchers be permitted to extract new, invasive samples from its base, potentially causing permanent damage, in the hope of uncovering one more microscopic clue? This tension lies at the very heart of modern conservation. The guiding principle here is minimal intervention. Conservators and heritage scientists operate under a philosophy akin to a doctor's oath: first, do no harm. Every action taken must be justified by a clear benefit to the object's long-term preservation, not merely to satisfy scientific curiosity. Non-invasive techniques, like the three-dimensional laser scanning and surface spectroscopy we discussed, are increasingly the first and preferred line of inquiry. They allow us to gather immense data while leaving the monument physically untouched, a digital handshake with the past that respects its material integrity. When any physical sampling is deemed absolutely necessary, it is done in microscopic amounts from areas already damaged or hidden, and always with the full oversight and partnership of cultural heritage authorities and local experts who understand the object's deepest significance beyond its chemical composition. This collaborative model is essential. The knowledge we seek is not just technical data, it is cultural heritage. The descendant communities and nations who are the stewards of these artifacts hold a vital, non-negotiable voice in how they are studied. True understanding comes not from extracting secrets, but from engaging in a respectful dialogue that honors the object's entire story, from its spiritual meaning to its role in a community's identity. This ethical framework extends beyond preservation into the realm of potential rediscovery. If the full craft of creating such enduring metal is one day successfully replicated, a new set of questions emerges. Who, then, owns this reborn knowledge? Is it the property of the scientific teams who decoded it? Should it be patented and commercialized by a corporation? Or does it rightfully belong, in a moral sense, to the descendant communities whose ancestors perfected the original art, a form of ancestral intellectual property? The history of bioprospecting and cultural appropriation offers clear warnings. Navigating this requires sensitivity and foresight. Any application of this rediscovered wisdom, especially for commercial gain, must involve fair benefit-sharing agreements and acknowledge the source of the inspiration. It is about moving from a model of extraction to one of partnership, ensuring that the pursuit of a lost technology uplifts and respects the living legacy from which it sprang. The goal is not to possess the past, but to learn from it in a way that is equitable, sustainable, and deeply respectful. The silent endurance of these ancient metals challenges us not only to solve a material puzzle, but to do so with a wisdom that matches their own timeless grace. The journey through fire and time brings us to a final, quiet reflection. Our exploration of this lost metallurgy reveals far more than a historical curiosity. It uncovers a true pinnacle of human ingenuity. Here, empirical craft and deep observation achieved results that still command our profound respect. We have stood beside the silent witness of the Delhi Pillar and stepped into the smoky forges of ancient masters. We have peered through microscopes at crystalline structures and pondered the philosophical choices of entire civilizations. At every turn, we saw a brilliant convergence, a unique chemical composition guided by masterful technique into a lasting harmony with its environment. These metals were not made to resist time, but to converse with it, achieving a state of equilibrium that allowed their message to whisper across centuries. This entire story serves as a humbling reminder. True progress is not a simple upward line on a chart. It is a complex landscape where peaks of extraordinary knowledge can rise, endure for an age, and then fade from common memory, obscured by the tides of economic change, social upheaval, or shifting priorities. The fragility of this profound understanding, dependent on the lived experience of a few and the stability of a cultural ecosystem, is a lesson in itself. It asks us to look at our own world with new eyes. What forms of deep, embodied wisdom do we value today? What are we in danger of leaving behind in our relentless pursuit of the new and the efficient? Let this mystery inspire more than just wonder for the past. Let it inform a more thoughtful approach to our own material future. The ancient craft points toward values we are urgently relearning: durability over disposability, sustainability through intelligent design, and a deep, respectful understanding of the materials we take from the earth. It champions a philosophy of building things that last, of creating legacies woven into the very fabric of what we make. This is not a call to abandon modern science, but to enrich it with these timeless principles, to seek a synthesis where efficiency walks hand in hand with longevity, and where our creations are partners with the natural world, not conquerors of it. If this journey through the secrets of rust-proof iron has captivated your curiosity, you are not alone. The past is filled with such enigmas, each a doorway to rethinking our present. Share your own thoughts and reflections in the comments below. What other lost technologies or ancient mysteries do you wonder about? For more deep dives into history's greatest puzzles, subscribe and join the exploration. The conversation with history is never truly over. It simply waits for the next curious mind to listen.